Hi, my name is Chris Riegel. I'm a data analyst from Wichita Falls, Texas, and today I'll be presenting a model that I developed with the purpose of predicting breast cancer based off of characteristics observed in tumors found on a number of patients. So the problem that we're going to be working on today is we have 2.1 million women affected in 2015 alone by breast cancer. Unfortunately, all of us probably know someone or have a friend or family member or even ourselves that have been affected by cancer. Breast cancer is the second deadliest cancer in women behind lung cancer. And most crucial to a positive outcome is early detection leading to early treatment and therefore effective treatment. So once someone unfortunately finds a tumor, medical professionals can use things like x-rays and MRIs to analyze different traits about those tumors and use those traits to determine the likelihood of it being malignant or hopefully it being benign regular growth. So the purpose of this analysis is to develop a model that is capable of taking information on traits observed by medical professionals and analyzing them and accurately predicting whether a tumor will be cancerous or whether it will be benign. Cool. For data collection and understanding, first of all, this data is secondary classification data. It comes from medical records, so observations from medical professionals that were put into a patient's medical records and then collected, and that came out of Wisconsin. There's 569 patients with confirmed tumors in this data set, and there are 32 attributes describing the tumor. The data was organized into an Excel spreadsheet with each row representing one patient, and then each column representing an attribute about the tumor. The second attribute in the data set was the diagnosis. It's going to be our target variable today, and it is nominal data. It's also binomial. The diagnosis is recorded as either an M for malignant or a B for benign. For preparing the data, the first step was to identify and set the ID. So one of the attributes was patient ID. It's a random number assigned to the patient for identification purposes only, and it holds no statistical significance to our analysis. So the data was imported into RapidMiner, and the set role operator was used to identify that attribute as an ID. Next, I went in and I checked for missing data, and I saw there was none, so that's good. All the data is there. We don't have to remove any patients for having missing data. I then used the detect outliers operator in RapidMiner, and I did find 10 outliers. So these outliers, for whatever reason that they may be identified as outliers, they can skew our data and affect the results of our model, so they need to be removed. So what I did was I used RapidMiner to export an Excel file showing the outliers, and then I used Excel features to delete those 10 patients that were identified as outliers, leaving us with a nice clean data set that is now ready to be imported back into RapidMiner and used to create the best model we can. To start developing the model, we again had to identify our dependent variable and our ID. So just like mentioned before, went back in and identified patient ID as ID, so that wouldn't affect the results of our model. And then I used set role as well to identify diagnosis as our dependent variable. I then had to use nominal to binomial to tell RapidMiner that, hey, diagnosis is a binomial, and to treat it as such, like I mentioned already, B for benign or M for malignant is how the diagnosis is recorded. Next, I needed a validation set and a training set of data, and I used the split data operator to do so that we could have our logistic regression be trained and then validated based off of the training to give us our best results. Finally, I inserted the logistic regression algorithm with apply model and performance, and I ran the model to see what results I would get. And here's what I got. Here's the confusion matrix. At the top left, we see that accuracy is 95.83%. It's very impressive. That leads us to a 4.17% classification error. So far, very high performing models is very good for us. The model also, if you look under the column of true M, that's true malignant, it identified 59 malignant tumors out of a total of 61 actual malignant tumors, which gives a 96.72% accuracy of identifying a malignant tumor. On the right column, under true B for benign, we see that it predicted 102 patients with benign tumors out of a total of 107 actual benign tumors. So it's 95.33% accuracy. So that's very good as well. More importantly to me is that it was more accurate with identifying malignancy, because that's what we're solving for. We want to get those people treatment soon, as they're the most at risk. Cool. With high performance, I still wanted to see if maybe there's a better model. Maybe there's a way to improve this model. So I used RapidMiner to give me a ROC comparison chart. So this was going to display the ROC chart, or the ROC chart for each of the selected algorithms. I selected decision tree, naive Bayes, logistic regression, random forest, and deep learning. And this operator gave me the product seen here that allows me to compare the ROC chart for each of those algorithms. And as we could see, they all appear to perform fairly well. However, logistic regression appears to be the highest performance, and therefore that's the one I decided to stick with. After deciding to stick with logistic regression, I decided to run a cross-validation to determine if possibly I could improve the model's performance even more. So I ran the cross-validation, and this confusion matrix is what it gave me. It gave me 92.32% accuracy with a plus or minus variable there. We have some predictability, as we could see in the confusion matrix, just like we saw on the first confusion matrix, and we see that it's not performing as well as the logistic regression that was previously set up with the split data set. I adjusted the folds and the sampling types, and I tried multiple combinations to see if I could tune the model, and there was no model of cross-validation that outperformed my original logistic regression. Therefore, I decided to stick with my original process, as it gave me the best performance out of anything that I tried. So let's take a look at some results. On the left-hand side, we see the ROC chart, and it is showing an area under the curve of 0.964. What this number means to us, an AUC of 1 would be perfect performance, and an AUC of 0.5 would be essentially random guessing. So closer to 1 we can get, the better that model is performing, and we see 0.964 is excellent performance, which is as we expected based off of our confusion matrix. On the right, we see the lift chart, for a simplified lift chart for this model, and it is showing us that for the top 30% of the data, the model is 94% confident or more, or has 94% or greater confidence in predicting malignant tumors. And again, I chose M for malignant because that is the target group of people that we want to be the most accurate with identifying. If we can identify those that have malignant tumors, we can get them, medical professionals can get them faster treatment and therefore a better outcome. One thing that I found interesting in my logistical regression and in my analysis was there was not a single attribute that showed statistical significance. So none of the p-values are going to be lower than 0.05. What does this mean for us? I think this means that it is fair to hypothesize that due to the complex nature of tumors and cancer and other medical problems, one attribute on its own appears to not have statistical significance. It's the presence of multiple attributes that leads to the diagnosis and the confidence of the model. Again, I'm certainly not a doctor or medical professional. This would require further research from medical professionals to confirm, but it is good to see this in the statistics to give an idea of what the model is seeing based off of the data set. All right, so the model performed very well. It's something that you could not beat the performance of the accuracy and classification error. So I was very happy with the performance of the model, but how do I want to deploy it? If I were to deploy this model, first thing I want to do is get this model into the hands of medical professionals right away so that they can use it in treatment. I would take the algorithm and the design of the model, put it into a product that's easy to use, such as maybe software that works well on an iPad or a doctor's laptop, depending on what the medical professional is using, so that they could take their observations and then quickly enter them into the product. And then with the model running in the background, pretty much right in front of the patient, same day, they could get a reasonably confident initial thought as to, is this patient at risk of having a malignant tumor? With that data in mind, they could then move to the center, which is faster treatment, where that patient has now been identified as possibly at risk, so that now the medical professionals can provide expedited testing and expedited confirmation of malignancy, or if the tumor is benign, and therefore I get treatment to that patient as fast as possible. Finally, that leads to saving lives. As I mentioned in the beginning, the most effective treatment for breast cancer is early identification and early treatment, which is going to lead to positive outcomes and successful treatment, ultimately save lives, and that's the goal that this model is trying to achieve. To improve this model, it comes down to more data. So we have 569 patients, which is a great start in it to train in the model. However, there's 2.1 million women affected per year. So more data is the key. The more data that's input into the model, the more the model will improve. The more has more data it has to learn from, and the more accurate it can be. Additionally, we had 10 outliers that were discovered in this data set. So why? What makes them outliers? Does that have significance? That's something to keep in mind. And as more data comes in, if we see more outliers, then we can continue to use the model to assess, is the fact that they're an outlier have any determination on their diagnosis. That's the model I developed. I enjoyed it, and hopefully it can be used to help people in the future. Thank you.